This lecture is about impulse momentum methods, but for rigid bodies. Okay, recall, you have the so-called impulse momentum relationship or impulse momentum theorem. Which says linear momentum final, total linear momentum final, minus total linear momentum initial equals the integral of from 0 to t or t1 to t2, however long is between final and initial. Let's just call it t1 to t2, t initial to t final. Sum of all forces on the system times dt. Okay, so this is called the impulse of all external forces on the system. And the system could consist of one or more objects. Okay, so that's the so-called impulse momentum theorem. And then we have the right-hand side can be 0 sometimes when, say, the sum of all external forces is 0, or when the integral is 0 for other reasons. For instance, when t final is basically the same as t initial and the sum of forces is finite, then the right-hand side is 0, right? So impulse equals 0 and linear momentum is conserved when, for instance, sum of forces, this is of course a vector, sum of forces on the system equals 0, right? So no net forces, like you're in outer space. Or case 2, sum of forces is finite. Example, gravity, etc. Gravity, springs, anything really, except the exceptions that we will talk about in a moment. And t final is basically the same as t initial, so that the integral goes to 0, right? So in other words, if you had a finite quantity and then you're integrating over such a short duration, of course the integral of a finite quantity over a short duration goes to 0 as the duration goes to 0, right? So these are the two cases in which the total impulse is going to be 0, and then in those cases linear momentum is conserved. Okay, this is the relationship that we wrote down for particles. This is a relationship that we wrote down for particles, and it's true for rigid bodies as well. Okay, let me use a different color. True for systems with particles, rigid bodies, whatever. Okay. It's even true for systems with deformable objects. Yeah. So this is a remarkably general relationship, and uh, it's only approximate to the extent that F equals ma is approximate. Okay. So that's the impulse momentum relationship. I said recall because this is the relationship that we wrote down for particle systems with particles, but then it turns out that the same equation applies for systems with rigid bodies or systems with deformable objects, including solids, liquids, and gases. Okay, so that's the impulse momentum relation. Basically, remains the same for rigid bodies, but the only difference is linear momentum for a rigid body. What is it equal to? If you had a single rigid body, so if you had a single rigid body, then of course its linear momentum is equal to if it had velocity v and mass m, and the velocity is actually of the center of mass. It maybe has some angular velocity as well, but the linear momentum is just equal to mass times the velocity of the center of mass. Okay, so only the center of mass matters for linear momentum. The velocity of any other point doesn't really matter. It's just the center of mass velocity that matters. Linear momentum equals mass times velocity of center of mass. And if you had multiple rigid bodies, it would be m1 vg1 plus m2 vg2, etc. For multiple rigid bodies. Okay, so that's the relationship. So we have this relationship, and then we know how to compute the linear momentum of a single rigid body. So we can apply those in various situations. For instance, problems involving collisions, etc. You can still use linear momentum conservation if one of these conditions is satisfied. Okay. So, well, let me just recap under what conditions sum of forces is not finite. Let me just briefly recall. So we discussed this in class when we were discussing particle mechanics. For the purposes of linear momentum conservation, infinite forces happen are forces of interaction. Let me actually in a collision, that happens over infinitesimal duration. Right, so basically T2 or T final almost the same as T initial. So if you have two objects colliding, we have forces of interaction, so basically equal and opposite forces on the two objects. F and minus F are basically infinite as Tf minus Ti goes to 0, while the objects still have their velocities change across a collision. Okay, so you can sort of think about why that might be true, right? So imagine two objects colliding. Imagine two objects colliding. A collision usually involves the velocity changing during the collision. And if the time duration over which the velocity changes becomes 0, what does that mean? You're having a finite velocity change in infinitesimal time. So what is the acceleration? The acceleration of these objects in that very small period of time is basically infinity as that small period of time goes to 0. So you're having infinite acceleration for these velocities during the collision, and that basically means that they are suffering from being acted upon by infinite forces. Okay, so these collision forces are generally considered infinite. So similarly, so the forces of interaction during the collision are infinite, but the forces of say external forces like gravity and or air drag or something like that on these objects may still be finite, right? So linear momentum may be conserved for the whole system, but linear momentum clearly is not conserved for individual objects. Okay, so that's a situation in which you might have infinite forces when you have collisions. Same analogous for explosions. Analogous interaction forces during explosions, which is the opposite of collisions. Explosions in which the component pieces experience a finite change in velocity in infinitesimal time. Okay, so imagine you have two objects stuck together, and then there's a collision where this is going in some direction, this is going in some other direction, and the forces between the two objects during the collision are what produces finite change in velocity. And if that finite change in velocity happens in basically infinitesimal time, then those interaction forces need to be infinite. Of course, in reality, these forces are not infinite, but just large. But we like to treat them as being infinite for simplicity. Okay, so that's linear momentum, still the same as before. The only minor change is that linear momentum now only worries about the center of mass for a rigid body. All these things were exactly the same as before as for particles. Okay, so that's linear momentum. We can take a look at how angular momentum issues change. So let's angular momentum and angular impulse. Okay, so if you have some system, some weird system with a whole bunch of forces perhaps, then angular impulse is the sum of all moments about some point, about, let's say, O dt integrated from t initial to t final, whatever the moments may be, about whatever point you're taking the impulse about. And then angular momentum again about some point, but let's first do about g, the center of mass of a rigid body. Is basically I g omega k in 2D. Okay, so it's basically I omega. I omega is basically angular momentum. So if you have an object, if you have a rigid body, if you have a single rigid body, and you have the point G, and this has some angular velocity omega k, then the angular momentum of this object about the point G is I omega k. Okay. Now that's the angular momentum of a single rigid body. If you want angular momentum about a different point, about a different point P, of a single rigid body, or for a single rigid body, and that's going to be equal to, it's rather similar to what we did before. So it's basically this term plus R G with respect to P cross M V G. Okay, so that's the angular momentum for a single rigid body. So if you have this rigid body and it has some velocity Vg and we have some point P, it's basically this expression is the angular momentum of the rigid body about the point P. So it's basically the angular momentum due to the rotation of the rigid body about its own center of mass, roughly speaking, and due to the linear motion of the center of mass. So those are the two terms here. Okay. This is due to the angular velocity. This is due to the linear velocity of the center of mass. So that's for angular momentum of a single body. Contrast this with angular momentum for a particle. Particle, let's call it G about point P. Okay, so you have some point P and you have, this is a particle G and it's got some velocity Vg. Then this is just equal to R G with respect to P cross M Vg, where this is the particle, right? So okay, so those are the revised expressions for angular momentum. This expression remains the same: angular impulse about O, angular momentum of a rigid body, about its own center of mass is this new expression. We've not seen that before. angular momentum of a rigid body about a different point is this expression. We've not seen that before. This is angular momentum for a particle about some point P. We have seen that before, and we can treat this as a special case of this expression where you essentially set Ig equal to 0. Okay? And then the main equation, how to use all this, is change in angular momentum of a whole system equals angular impulse. Then exactly under this sort of similar conditions to linear momentum, you can have angular impulse go to 0 under a variety of conditions. A condition where the sum of moments equals 0, or so this is the same as before, angular impulse equals 0 if we have a few situations of sum of all moments external moments equals 0, if sum of all moments equals 0 about, well, let me unwrap this thing. Sum of all moments about the point P or whatever point you're going to take moments about. So sum of all moments can be 0 if due to forces, no forces on the object, or just forces all pass through point P about which you're taking moments. So this is the so-called central force problem. Or the forces somehow produce moments that just cancel each other. All those are possibilities. That's also a possibility, but it's not a simple possibility. Or you can have angular impulse equals 0 if sum of moments equals finite, but Tf minus Ti basically goes to 0, so that integral sum of moments dt equals 0, okay, or goes to 0. Okay, so those are basically our key relationships and theorems and physical laws that we shall use to examine objects, say colliding or undergoing other velocity changes due to the application of forces or application of moments. Okay, so let's see a few examples of that nature.